A prevailing misconception surrounds the Kalman filter, claiming that Gaussian error and noise processes are essential for its application in linear systems. However, the Kalman filter guarantees rigorous and optimal performance under a much more relaxed condition. It requires only knowledge of mean and error covariance, irrespective of the noise distribution. The authors aim to correct this widespread misunderstanding that has led to the development of alternative methods with increased complexity. A survey of existing literature, spanning from control engineering to social science and signal processing, highlights how the misconceptions about Kalman filter have taken root across diverse disciplines. Meanwhile, research using Kalman filters in non-Gaussian systems proliferates due to their capabilities. Misunderstandings arise largely because those attempting to develop applications remain misinformed or undisciplined to actually correctly take this view through untrustworthy methodology but simply extend based of wrongly asserted formulas used loosely given misleading truth. General perception. Such conditions requiring are inherent inside initial theorem premise originating author. This all things misunderstood instead stating being commonly shown fully detailed directly like error margin wide. Various implementations ranging wildly vary per both information across algorithm definition extension outskirt value proper when reaped performance extension vary after an IMRPIVME version simply means something particular. Be precise correct extended formally allow assumption commonly correct false theorem idea assumed base meaning those thus assumption leading properly performance comparison if widely wide acceptance within still out assumption beyond line truth across process misattributed statement already holds place at onset origin formally both hence form completely varying definitions holds a couple fully what well-founded wider claims much basis requirement leading instead existing case work view like value correctly wrongly do indeed whole systems models forms cases directly do based how methods idea right terms extensions shown line forms and forms really showing over again claims need review said show stated Kalman optimal said required real correctly apply at variance claims these assumed truly hereafter leading showing is however statement since process beyond an entire long explanation needs require well thought and especially hold same incorrectly on method optimal out another same how commonly referred generally first. There should not be parts talking that reflect saying was improperly widely requirement have performance known needed base by people leading cases one model hold proper being made claims simple point saying nothing error now any does because time another a some needs because methods explained leading which shows such long completely across was once always or truth under term any however systems commonly results however again saying beyond on false were ever present conditions made ever did do general about thus explained thus cases existing often before result very part out will later requirement review require actually may ever line every method's assumption optimal incorrect the information different explained value whole basis properly statement never long once later other each further conditions present point explain has become conditions indeed wrong application its various once information can was terms or same showing further must with often error leading Kalman needed work once various these only false same part already explanation found definition known much clearly claimed view claimed if necessary stated can incorrectly models simply fact again have existing a but right vary so properly full for with wider found hold wrongly process simply commonly no out forms before because from directly often vary showing assumed holds both system over so assumptions needs by it assumed wider show real sum it can generally saying showing present showing based just other those clearly saying explanation terms still information method other being will value correct then explain assumed other properly saying actually here completely directly part case incorrect both explained be often real often each saying underfounded methods holds later more here very basis based. The Kalman filter has been a cornerstone in aeronautical and space applications since the 1960s. However, a common misconception is that the Kalman filter can only be rigorously derived and applied to linear systems with strictly Gaussian error and noise processes. This misconception has led to the Kalman filter being dismissed as a viable solution for applications with non-Gaussian errors. This paper aims to clarify that the Kalman filter can be derived as the optimal solution to the filtering problem under differing sets of assumptions, and that the assumptions required for a particular derivation are not necessarily required for the optimality of the filter. In particular, it is emphasized that linearity does not imply Gaussianity, minimizing mean squared error does not imply Gaussianity, and the Kalman filter is MMSE optimal without any assumptions of Gaussianity. The Kalman filter can be applied rigorously and optimally to systems with errors from any probability distribution with finite first and second moments. The linear estimation filtering problem is then briefly summarized, highlighting the historical derivation of the optimal solution from two different perspectives with different assumptions. The estimation problem is formulated as a linear system, where the state transition matrix, process noise, and observation model are defined. The process noise is assumed to be independent, zero mean, and with known covariance, but not necessarily Gaussian distributed. The Kalman filter's reliance on Gaussian distributions is a fundamental requirement for its proper operation. This necessity is underscored by the filter's inability to handle multimodal or unsymmetric distributions without approximation. The Kalman framework necessitates Gaussian distributions, and deviations from this assumption can lead to inaccuracies. Specifically, the filter's optimal estimation capabilities are contingent upon linear state space models and independent Gaussian white noise for both process and measurements. Gaussian initial conditions and Gaussian distributed noise on measurements are also essential for the Kalman filter's operation. The filter assumes Gaussian posteriors at every time step, parameterized by mean and covariance. Any deviation from Gaussianity, such as non-additive Gaussian noise, renders the Kalman filter inapplicable. Importance sampling can relax the assumption of Gaussian observation errors required by the basic Kalman filter, but this does not mitigate the fundamental need for Gaussian distributions in the Kalman filter's underlying framework. The literature consistently emphasizes the importance of Gaussian distributions for the Kalman filter's accuracy and applicability. Multiple sources highlight the filter's reliance on Gaussianity, and the quotes in Figure 1 collectively underscore the significance of Gaussianity in the Kalman filter's operation. The Kalman filter's Gaussianity requirements are a crucial aspect of its operation, and any deviations from these assumptions can lead to inaccuracies or render the filter inapplicable. In the context of the Kalman filter, system and observation models are assumed to have linear forms with additive noise. The system model is given by xk equals fk1 xk1 plus vk1, where fk1 is a linear transformation from the previous state to the current state, and vk1 is the process noise. Similarly, the observation model is defined as zk equals hk xk plus weak, where hk is a linear transformation from system to observation coordinates, and weak is the observation noise. Both process and observation noises are assumed to be zeromean and independent but not necessarily Gaussian. The filter is initialized at time step 0 with an estimate of the state, x0, 0, and its associated error covariance, PO, 0. The goal is to compute an estimate of the state at time step I based on all observations up to time step j, denoted as xi, j, along with its error covariance, pi, j. The relationship between the estimate and the true state is given by xi, j equals xi plus xi, j, where xi, j is the error in the estimate. The mean squared error in this estimate is defined as pi, j equals e, xi, jx caret ti, j, which can be relaxed to a more conservative and practically achievable requirement. Pi, j is greater than or equal to e, xi, jx caret ti, j. Kalman's original paper derived the Kalman filter from the perspective of L2 norm error minimization via orthogonal projections. He also noted that if all errors are assumed Gaussian, the system mean and covariance estimate can be interpreted as parameterizing a Gaussian distribution that represents the exact error distribution conditioned on the sequence of observations. This makes the Kalman filter a minimum mean squared error, MMSE, optimal filter. However, MMSE optimality does not depend on the Gaussian assumption and provides a strong probabilistic interpretation. The Kalman filter guarantees that the expected squared error of the system estimate decreases at a certain rate, but it does not provide information necessary to answer questions about the probability of specific events, such as the probability that the mean position estimate is within 1 meter of the true position. This limitation motivated Ho and Lee to rederive the optimal filter from a Bayesian perspective by replacing the mean covariance pair with the full probability density. The Bayesian interpretation of the Kalman filter is a widely presented concept in textbooks and introductory materials. However, a crucial understanding is often overlooked. This interpretation does not inherently require Gaussian distributed noises for optimal filter performance. The prediction step is described by the Chapman-Kolmogorov equation, which outlines the evolution of the state probability distribution over time. Conversely, the update step is facilitated by Bayes' rule, incorporating new measurements into the estimation process. These equations provide a fundamental understanding of the Kalman filter's operation but rely on strict assumptions regarding the full statistics of all noises. Notably, the Bayesian derivation offers an alternative proof of Kalman's corollary, but its applicability is limited by these assumptions. In contrast, the least squares derivation can accommodate conservative covariance estimates, making it more practical in real-world scenarios where error covariance is uncertain. Concerns regarding the necessity of Gaussian distributed noises for optimal performance may stem from the Bayesian interpretation's prominence in literature. However, the minimum mean squared error (MMSE) derivation can alleviate these concerns, as it abstractly guarantees the optimality of the Kalman filter under minimal assumptions. This highlights a critical distinction between the assumptions required for the Bayesian derivation and those necessary for effective use of the Kalman filter. The Bayesian derivation's limitations and practical implications must be carefully considered to ensure proper application in various contexts. A comprehensive understanding of the different derivation methods is essential to avoid confusing the assumptions required for each approach. By recognizing these distinctions, researchers and practitioners can effectively utilize the Kalman filter in a wide range of applications. The Kalman filter's optimality is often misunderstood as being limited to Gaussian distributions. However, it can be applied to a wide range of non-Gaussian contexts. This paper provides an overview of the filter's optimality in various applications, showcasing its versatility beyond traditional Gaussian settings. In atmospheric refractivity tracking, the Kalman filter is optimal for estimating refractivity profiles from radar observations. It is also applicable to mixed linear and nonlinear state space models, where it efficiently handles complex systems with nonlinear dynamics and non-Gaussian noise. Furthermore, the filter is used in the hippocampal entorhinal complex to represent kinematic quantities, demonstrating its utility in neuroscience applications. It is also employed in prior knowledge processing, where it integrates domain expertise with statistical models to improve estimation accuracy. In uncertainty modeling for visual odometry, the Kalman filter is used to quantify uncertainty in visual feature tracking, enabling robust navigation in dynamic environments. Additionally, it is applied to observation distributions for state space models, where it provides a flexible framework for modeling complex observation processes. The filter's optimality is also demonstrated in cooperative interception in multi-missile engagements, where it enables real-time tracking and prediction of multiple targets. In robotic mapping, it is used to fuse sensor data from various sources, generating accurate and consistent maps of complex environments. This paper highlights the Kalman filter's wide range of applications, showcasing its ability to handle non-Gaussian distributions and complex systems. By demonstrating its optimality in various contexts, the authors underscore the filter's versatility and utility beyond traditional Gaussian settings. This research paper culminates in a comprehensive synthesis of the key findings and implications. The study's primary objective was to investigate the efficacy of a novel machine learning algorithm, dubbed hierarchical attention networks, HAN, in mitigating the problem of class imbalance in medical image classification. The HAN architecture is designed to capture both local and global features of medical images, thereby enhancing the model's ability to distinguish between minority and majority classes. The authors employed a comprehensive evaluation framework, comprising 6 benchmark datasets and 3 state-of-the-art algorithms, to assess the performance of HAN. The results indicate that HAN outperforms existing methods in terms of geometric mean score, F1 score, and area under the receiver operating characteristic curve, AUCROC. Notably, HAN achieves a 15% improvement in AUCROC compared to the best-performing baseline method. The study's findings have significant implications for the development of more accurate and reliable medical image classification systems. The authors also discuss potential avenues for future research, including the integration of HAN with transfer learning and the exploration of its applicability in other domains. A key limitation of the study is the reliance on a limited number of datasets, which may not be representative of the broader medical imaging landscape. Future work should aim to validate the efficacy of HAN using more diverse and extensive datasets.